In this video, I will show you how to simplify radical expressions such as these, even ones that have a negative under the radical. When I look at problem number 1 and I see that there's a negative under the radical, I know that there's going to be I at the end of this. So I'm going to ignore that negative sign for now and just simplify the square root of 525, and I'll just stick an I in there because this will be imaginary. Now, there are two methods for simplifying a radical. One is a method that you can use when the numbers are small and obvious. For example, if I have the square root of 18 and I want to simplify that, I can look at that and know that there's a perfect square of 9 that is a factor here. So I can split this apart as radical 9 times 2, because 9 times 2 is 18, and then the square root of 9 is 3, so I would have 3 radical 2. If this were negative, this would be 3i radical 2. Now I can just do that in my head because the numbers are small. When the numbers are bigger, like 525, I like to use another method involving a factor tree. So if I take 525 and I'm going to break this down to its prime factorization using a factor tree. So I know that obviously 5 will divide evenly into this. So I'm going to split this apart as 5 times something. Now here's where I will use a 4-function calculator. Now this is actually a scientific calculator, but let's pretend that it's a 4-function calculator, because that's all you will be allowed to use. So 525 divided by 5, that's 105. Okay, so this is 5 times 105. Now this is a prime number. Now I can keep going here. 5 divides into this evenly, so I can take my 105 and divide by 5 again, and that's 21. So this is going to be 5 times 21, prime number. Now 21, this is one of our multiplication facts. We know that this will be 7 times 3, and these are all primes. Okay, so the prime factorization of 525 is, and I'm just going to write it in order, so this is going to be 3 times 7 times 5 times 5. Okay, that is the prime factorization. Because of the negative, I'm going to go ahead and put the I. Now, this pair of 5s is a 25, and the square root of 25 is 5. So on the outside of the radical, this is going to become just a single 5, because the square root of 25 is 5. So I use these pairs to become a single. Now, when there are no pairs, that means those numbers will be left inside the radical. So this 3 and the 7 are not going anywhere. So that's going to be just the 21 is just going to be left inside. So the final answer will be 5i radical 21. Okay, so I call that the prime factorization method. And that's what I always do when the numbers are larger. Okay, so again, looking at problem number 2, I see that negative sign, so I know there's going to be an I involved. 567, that's pretty big. Okay, so I'm going to do the factor tree method to get my prime factorization. Now, I briefly added up these digits, and these add up to 18. The reason why I did that is because that tells me that this number is divisible by 9. Okay, if you add up the digits and it's divisible by 9, then the original number is divisible by 9. Okay, so that tells me, let's see, 567 divided by 9, 4-function calculator. That is 63. Okay, so this is going to be 9 times 63. Okay, now I could break this down. You know, if I use my prime factorization method, I would go 3 times 3. Or I could just leave it as a 9 because it's already a perfect square. But I think I'll just follow the procedure that we were doing just to show you that it always works. And then, of course, 63 is 7 times 9, or 9 times 7. So this is a prime number. And again, I really could just leave these as 9s, or I could go ahead and write 3 times 3. I'm going to go ahead and just follow the procedure, so I will go ahead and break it down to 3 times 3. Okay, so the prime factorization here is going to be 3 times 3 times 3 times 3 times 7. That's the prime factorization. Because of the negative under the radical, it's going to be I. And of course, this pair of 3's is the 9 that we saw right there. And the square root of 9 is 3. So I will have 3 on the outside. This pair of 3's is another 9, which we see right here. So the square root of 9 is 3 on the outside. The 7 is a single. So that's just going to be stuck underneath the radical. So that's why in the final answer, 3 times 3 is 9. So I'm going to have 9, and I will have radical 7. And then I'll just go ahead and bring in the I. So the final answer here is going to be 9I radical 7. Okay. Now, when you have a fraction underneath, you can split it apart this way. This is the same thing as the square root of 49 over the square root of 3. Now, this happens to be a perfect square, so I'm going to go ahead and say 7 over radical 3. Now, you never want to leave a radical in the denominator. So what you can do to simplify this is just multiply by the denominator. Okay, because radical 3 times radical 3 is regular 3. Right? Because this would be the square root of 9, which is 3. And in the numerator, now I have 7 radical 3. So this would be the final answer for problem number 3. Okay. Now, really, this fraction can be reduced. So before I do anything else, I'm going to reduce this fraction. Okay. It looks like both of these are divisible by 4. So I'm just going to divide by 4 to reduce this fraction. So 4 function calculator, 128 divided by 4 is 32. That tells me that really both of these are divisible by 8. In fact, maybe I'll just follow through for a second. So this fraction would be, so I would have been 32 divided by 2. But 32 divided by 2 is 16. Okay, so I have if it's just reducing this fraction, I have the square root of 32 over 2, or the square root of 16, which of course is 4. So the final answer here is going to be 4. Now that I see the smaller numbers and how it worked out, I'm realizing that 128 was divisible by 8 in the first place. So 128 divided by 8 is 16. Okay, so if you just do the division in this case, I could have gone straight to here and saved myself a step. But sometimes you don't see the full picture right away, and you don't notice until later. Okay. I'll go ahead and include these last two problems in this video. Write the complex number in standard form. Now, if you just have a radical, there's no sum or difference. It's really not going to be any different than what we were doing up here. I see the negative, that's going to be I. So ignoring that for a second, radical 99 is the same thing as the square root of 9 times the square root of 11. All right, 9 times 11. Okay, that negative is going to be an I. The square root of 9 is 3, so I have 3 radical 11, and the I goes in the middle. Okay, so that's all we can really do with number 5. Okay, when they talk about a complex number in standard form, they are talking about this. All right, standard form of a complex number is A plus BI. But this expression only has an imaginary part. There's only a term that has an I in it. There's no other term, so we just leave it like that. Okay, so looking at number 2, looking at number 6, let's go ahead and simplify the square root of negative 27. So obviously the negative sign is going to give us an I. So ignoring that for a moment, 27 is 9 times 3. Okay, so I know there's going to be an I in there in a moment. Square root of 9 is 3, so that's going to give us 3I radical 3. And I'll just bring down the 2. And so that's it, 2 plus 3I radical 3. That's your A plus BI. Okay, that's as far as we can go in this video because we're about to switch over to a different topic. So I will see you on the next video if you want to see how to add and subtract complex numbers. All right, things such as this.